Make sure I've actually got the microphone on. Yeah, so hopefully you guys should be able to see the screen. Yeah, welcome to our event tonight on Astrodynamics and Space Robotics Lab at UCF. Looking forward to hearing about the cool work those guys do over there. A few AIAA updates. For those who are not familiar with our organization, the American Institute of Aeronautics and Astronautics is the largest professional organization in the aerospace industry. We have members from all over the place. Pretty much every aerospace company or school has people involved in it, anywhere in the world, really. Here in the Central Florida section, we have local events like this to showcase some of the awesome stuff we have going on here in Central Florida, as well as to provide services and activities to help our professional, student, educator, and retiree members here, as well as our student branches at UCF and UF. We do actually have a project funding application and a scholarship available this year for student members. So if you're a student AIAA member, reach out to your local schools section there, and they can help you get a hold of that, or you can contact us at the Central Florida section. We do have some other upcoming events. AIAA Ascend is the biggest space forum that AIAA is hosting now. That actually started this week virtually. The main event is going to be next week, the 15th through 17th. So if you're a student or a retiree, they have really good rates for you guys. Definitely would recommend checking it out. I think the student rate is $65 for virtual attendance. So that's pretty good for a full 3-day conference. Professionals, it's a little expensive, but my company offered to send me this year, so I'm really excited to get to go see that stuff. Always a lot of great presentations. We also have the Sun and Fun Holiday Fly-In Festival and Car Show coming up. So that's hosted by Sun and Fun in Lakeland, here in Central Florida. And we got 25 tickets to give away to our members this year. So we're really excited to have that. We have given away most of them. We have a few left. So if you're a member, you should have got an email about it. Make sure to check your email in your spam folder. If you didn't get your email, let us know after the event tonight, and I can send the link to you to apply. We have, I think, 3 tickets left. If you don't get a ticket, it's only $12, so it's still not too expensive. It'll be a really fun event to get together and just hang out after 2 years almost of not having any in-person events. So we're looking forward to that. We also have a glider competition we're hosting for SCCME, which is a volunteer event. We're helping K through 12 students learn to build gliders. In February, we'll need some volunteers for that. So if you're interested in coming out to UCF and helping us out, doing a glider competition for kids, it's going to be a lot of fun. We'll basically just be throwing gliders and measuring distances and things like that. Yeah, let us know. We're glad to have anybody come and help out and check out the event. We'll also have a resume and interviewing workshop coming up in January, so that'll be virtual, probably the second week of January. We'll have a link sent out for that soon. And monthly council meetings. We meet every month to talk about AIAA and the stuff we're going to do here in Central Florida. So if you're interested in getting more involved, everybody's always welcome to attend. Just let us know, and we'll be happy to send you the link. And we're always looking for cool speakers. So if you have a cool topic you'd like to see or talk about or anything like that, be sure to let us know. Yeah, stuff like this is always great to see what's going on here in Central Florida. If you want to learn more about our organization or have any questions or anything, you can always contact us: Facebook, Instagram, YouTube. This event, as well as a lot of our previous ones, are also on YouTube. So you can go check out the Dragonfly mission to Titan. Dr. Ralph Lorenz, that was a great presentation earlier this year, as well as our previous interviewing and resume workshop. So some great resources you can access all year. And that is all I have. So I'll hand it over to Dr. Tarek.
All right. Well, thank you so much. And I'm definitely excited to be here with the Central Florida section. Uh, so today let me share I'm not sharing my screen, am I, right? There we go. Right. All right. So are my slides showing? Okay, perfect. So today I'll be giving an overview about some of the research activities we're doing at my lab, Astrodynamics, Space and Robotics. And I know we don't have a lot of time, so I'll be focusing more this evening on the astrodynamics research, and I'll give a few glimpses on the space-related and control and robotics as well related research towards the end of the talk. Each of those topics are very, we have various activities going on in them, and it's hard to put all of that stuff in 1 hour, to be honest. So, but I'll give you an overview of what's going on my lab. A little bit about me is that I graduated with a bachelor's in mechanical engineering. Then I got my master and PhD in aerospace engineering. I did a year of a postdoc, and then I became a professor, an assistant professor at UCF since 2016. Uh, as I said, the research areas that I'm working on are astrodynamics, space situational awareness, uh, multi-body dynamics related to lunar dust, and finally controls and robotics in aerospace applications. Some of the courses that I taught were obviously astrodynamics, guidance, navigation control, vibrations control, dynamics, and control. So that's a very quick overview about what I do and about myself. So this picture shows basically the three areas that we're working on in my lab. And although they might look a little bit disconnected, but they are actually all connected through nonlinear dynamics control and computation methods. So in astrodynamics, we're looking at space-based surveillance systems or space-based orbit estimation. We're also looking at accurate uncertainty propagation techniques. Those two have elements of guidance, navigation, control, as well as computational techniques. For the space portion of the research, which mainly focuses on dynamics of charged lunar dust, basically it revolves around looking at multi-body dynamics and using a specific set of computational techniques to solve these problems, model and solve these problems. And finally, the controller robotics is related to has a portion which is related to real-time optimal guidance, and another portions where we do hardware experimentation for various space applications. So the common denominator in all of these is the research we do in nonlinear dynamics, control theory, and computation methods. And that is sort of what holds all of these seemingly disparate research topics together. So I'm gonna give most of my talk about the astrodynamics research going in the lab, and then I will give an overview, a little bit of an overview about uh, the other two areas where we have lunar dust dynamics and optimal control and robotics. And this is just a quick historical overview that I give in my classes, and some of the audience here are my students, so they probably have seen this before. So that's a quick overview of the history of celestial mechanics or astrodynamics as we know it now. Several contributions. The main ones, you probably heard some names like Kepler, Newton, Euler, Lagrange, and Gauss. And most of the earlier, obviously, contributions were related to celestial bodies. Later on, the astrodynamics came in view, and astrodynamics described man-made presence in space. So man-made objects in space, whether it's controlled debris, because this is something we're suffering from right now, controlled spaceflight missions, trajectory design, and so on and so forth. And most of that falls under astrodynamics. Several of the modern or contemporary major contributors in this area is Sam Herrick, which is my advisor, and Richard Batten, who passed away 4 or 5 years ago, and and Mueller, and then my advisor, Jean Jenkins. So those are main areas or main people that worked in these areas of astrodynamics. The motivation behind doing research in astrodynamics is sort of a coupled problem of an increasing debris population in the various space orbit. And these pictures below are basically from NASA space debris. We basically track space debris, and you can see there are some events that took place due to collisions or experiments that caused a jump in the debris population. Now, there is a theory out there that's called Kessler's syndrome that says that more debris will collide and disintegrate, causing more debris to exist. So essentially an exponential growth in debris. The other part of that problem, so we have here what represents an increasing population in space debris, and potentially, as you can see here, the plots, it shows an increasing trend in the various the various Earth orbits. Whether that being more dramatic in Leo orbit, but it exists in the various bands of Mio and Geo as well. So um, and as I said, the fact that there is something called Kessler's syndrome or Kessler's theory is that these objects will keep colliding with each other, producing more objects with a prediction of exponential growth of debris. The other aspect of that problem is that the two-body problem or the governing equations, which is the part of the nonlinear dynamics aspect of the research we're doing, is essentially a nonlinear problem, highly nonlinear problem with several perturbations. Just the two-body problem here, and this is, what describes the interaction between two masses and distances between them. You get this inverse quadratic gravitational law that we all know and love. And also, on the other hand, the uncertainties, because of the nonlinearity of the problem, if you started with this dot of distribution, of initial distribution of particles after one orbit, this is the distribution you get after one orbit around the Earth. And this is without including any perturbations or even uncertainties in those perturbations. So the orbit problem is nonlinear by definition, and it basically affects the propagation of the uncertainties as we go forward in time. And that's why we are studying these problems, why we're developing methods to, number one, better identify objects in orbit, and number two, how to essentially propagate those uncertainties accurately so that we get better orbit predictions uh, in the absence of measurements. So the first aspect or the first part of this would be related to space-based orbit estimation. Now, the current state of the art or the current approach of doing orbit estimation is this. There's the Space Surveillance Network, which has several ground stations and a very limited number of space-based observers. This is basically managed by now Space Force, and essentially tracks all objects, not all objects, like that population of objects. Now, this is about 20,000 objects if you added all of them up together. You're talking about 20,000 objects that are trackable. These are usually about 10 centimeters in diameter, so a size of a baseball. Populations that are, no one knows, to be honest, the actual numbers of populations below that number. So some estimates says we are between 1 centimeter and 10 centimeters. We are talking about 500,000 objects, and below 1 centimeter, we're talking about millions of objects. So no one is actually tracking those. Now, if you're following the news, there has been a couple of ISS encounters with debris, and some damage were done on some of the solar panels of the ISS. So it's a problem that can actually jeopardize existing satellites and can even jeopardize lives of astronauts in the ISS or scientists in the ISS. So one area that we're looking at is space-based orbit estimation. Now, this area had been looked at, and there's another name for it called space-based surveillance systems. And this area has been looked at for quite some time, and it suffered from some deficiencies. Is that there's an ambiguity when you take measurements in space without range. Like if you're using a camera, you don't get range information. And if you don't get range information, this problem, there is a problem about it introduces an ambiguity, or in other words, an observability problem of the object, which essentially affects the estimation. Now, this has been tried to be resolved several ways using thrust to essentially modify or take measurements from different perspectives using stereo cameras and so on and so forth. But each type of camera can essentially look at a specific or each solution we're using a specific way of measurement, and there was no way of unifying all of these measurements to produce better results. Now, what we have looked at is coming up with sort of a unifying measurement model. That unifying measurement model essentially it was motivated by the angles only measurements, so by monocular camera measurements, if you will. And this is where a lot of math would start. So hopefully it's not too much. But the basic idea is quite simple, is that you can use intersecting planes to define a line and use intersecting lines to define a point in 3D space. Now, that combined with the fact that you can have measurements from different objects is what motivated, or sorry, different observers, is what motivated our research. So if you look at, a very simple representation of an observer spacecraft, which measures two angles measured or shown here as azimuth elevation in the body frame, then you go through some coordinate transformation to move this measurement in an inertial frame. So you go from body to the orbit frame, or the radial along track and cross track frame, or the Gaussian frame, and then finally you go through to the inertial frame. So once you have these measurements in the inertial frame, you can start defining line of sight sequences, or you can start defining line of sight vectors. So from one observer to the target, from the second observer to the target, from the nth observer to the target. These are vectors that define line of sight, or that represent line of sight. Using that line of sight vector, you can represent there is an assumption, obviously, that we know where the observers are. We have certainty in the position of the observers. And then we can essentially define the observer unit vector from the 0, which is the inertial frame centered in the Earth, and observer 1 through observer n. Having those set of vectors, we can start constructing planes. So remember, the original idea was that we need to do intersecting planes, or we need to construct intersecting planes, and then we construct intersecting, from this, we can construct intersecting lines so that we pinpoint the target in 3D space. So first, we define a couple of intersecting planes, and we essentially start to look at their intersection. And what we can end up with after some rearrangement is this matrix in this yellow or yellowish orange box, which essentially represents the input from each separate observer in a measurement model that looks something like a measurement y is a nonlinear function of x being the unknown state of the target. Now, I'm showing this structure because it's quite important in our idea. Is that once you have this structure, it doesn't matter if you're measuring angles only, or range only, or range and angles, or any combination thereof of measurements, because each observer contributes to that matrix by this block sub block matrix, as you see here. So now you can add and remove measurements as you see fit, depending on their availability, whether they are good or bad, whether they are of the same type or different type, or whether they are synchronous or asynchronous. So that becomes a very versatile measurement model that can accept or that can unify measurements taken from different observers using different sensors. Here we're focusing more on angles only because that's part of the set of results I'm showing here, but the model is quite versatile and can accept different measurements from different sources. Now, after you do this, you have this structure where you have a nonlinear measurement model that can be fed into a simple, for now, a simple Kalman filter. With the Kalman filter, you see, if you're not familiar with the Kalman filter, you essentially start with a guess, compute some gain that essentially is used to update your state and error covariance. And we will talk about this later because this error covariance essentially gives you an idea about the uncertainties in your model. And afterwards, you propagate the dynamics and the covariance, and then recompute the gain, update, propagate. Each time you do this step is that you're inputting a new set of measurements. And each time the time as time goes forward, you're essentially obtaining a more accurate result about the orbit. Now, as you see here, we have to initialize that filter. And to initialize this filter, we modified a known method for initial orbit determination to include inputs from different observers or from n observers, essentially. In this case, we are representing a modification on a method called Harry-Gibbs that takes three measurements and essentially estimates an initial position and velocity. This way, and as you can see here, there is some linearization going on in the filter where you are using the Jacobians. So this way you're close enough to a good initial guess, and the filter would converge fast. Now, we have done some studies about how or by how much results improve as you add or remove observers. So obviously, given the theory that we are basing this off, the minimum number of observers is 2. Adding a third observer obviously buys some accuracy. Adding a fourth observer is not very obvious if you need a fourth observer in terms of the RMS error and in terms of the overall filter behavior. So you can see there is a very similar behavior between 3 and 4 observers, albeit there is an improvement, but it is not that that significant. So we did some studies to see how many observers we need and what would be an acceptable number of observers to obtain good results. The other effect or the other area is that a filter, if you introduce bad measurements to the filter diverges, and that is universal. Any filter, if you introduce bad measurements, it diverges. Now, in our study is that we needed to define what are bad measurements in that context. What would entail a bad measurement? And for that, we used this idea of observability. This set of results is based on an analysis that links observability or the instantaneous observability with the accuracy or defines what is a good or a bad measurement. And for that, we essentially came up with, sorry, I'm going to, yeah, we essentially came up with a scheme where we can exclude a measurement. As you can see here, we came up with a threshold on the condition number for this specific research. And essentially, this threshold defines what a bad measurement is. So now you can see here, we start with 4 observers. When we reach that threshold, we turn off one of them, and then we turn it on again. And you can see the effect of this approach on improving the filter results. So as you can see here, the previous one, the filter diverges, and here it's in a much better shape, essentially converges to the previous levels of accuracy, which is something that is enabled by the fact or by the structure of this measurement model. As you can see here, all we need to do is just remove one of these sub-blocks and essentially keep going with our filtering scheme right there. And when the fourth or excluded observer becomes available back online, we add its subblock and essentially improve the results. Now, this could also be said for tasking. I could essentially turn off one or two observers out of the four. Let's assume that the four are all doing well and producing good results and do not have an observability issue. I could choose to select to turn off to basically turn their attention to another object that they need to track. As long as I have two looking at an object, I still can get very good estimation results. So that versatility is enabled by the measurement model, and essentially it can be turned on and off depending on the uh, a bad input that will cause the filter to diverge, or tasking. Because later on, what we found out, and I'm not showing those results here, they found out that we can actually adapt the measurement model. So we avoid this singularity or this jump in the condition number. So we moved on to applying this on a constellation. And this is not an optimized constellation. This is a standard Walker constellation looking at the sky. And a Walker constellation is what you see here in these crisscrossing path of a couple of thousand satellites. So this is not optimized at all. It is just a representation of a constellation that could be used to track debris in an Earth orbit. And you could see here now, we included another factor, which is Earth obscuring the object. Because you see here, some of the path are on the other side of the planet, assuming that the planet is in the center of all of this. So if you look at this, this plot here shows how many observers are being utilized throughout the whole simulation time. And there was a limit on limitation. There was a limitation on the range. There was also a limitation on Earth being in the way. And we could also add several other limitations. And also we could also add tasking. In addition, in this simulation, we also had the condition number threshold. So here we only consider three factors: range, Earth, and the condition number, which essentially exclude bad measurements. And you can see here how the filter behaves, or how we can include and exclude measurements in or observers as we go forward. And the results are, as you can see here, are very good. We talk about meter accuracy of position and velocity, and a good sensitivity result. Then we move to, so here, the assumption here, although it might not be showing because of the scaling of the plot, but this is circular orbit. The target has a circular orbit. In astrodynamics, as you increase the eccentricity of the orbit, you increase the difficulty of the problem, you increase the nonlinearity of the problem. So here we introduce a slightly eccentric orbit, a 0.1 eccentric orbit, which is not a small eccentricity. Most of Earth orbiting satellites in LEO has a lower value than this, but still not a very high eccentricity as well. So we introduced the 0.1 eccentric orbit, and again, you could see here that because of the eccentricity and the various constraints we put on the filter, the number of observers that are being utilized has dramatically decreased. However, we're still within the same order of magnitude of estimating position and velocity. And you can see that the filter behavior here, especially in these increasing gaps of no measurements. So you could see here that the bounds, or these red lines, describe the uncertainty bounds of that filter, that the filter is getting or moving towards divergence. But once we start picking measurements again, it quickly converges and finally converges to the final, to the accurate state estimation. So that also is a function of the robustness of the proposed or the shown measurement model. So as you see here, the filtering problem has uncertainty embedded in it. So this is basically the second part of this astrodynamics research, is that as you increase as you see here, these uncertainty bounds are also an intricate part of the estimation process. And that gives me the confidence levels of my estimates. So sources of uncertainty in the orbit problem in general can be divided into a couple of things. It could be divided into the state uncertainties. And this is how the uncertainties surrounding my best guess on the current state, position and velocity in inertial space of a target or of an object in space that I am tracking. And essentially in the filter, this is what this is. This is the red dotted line that essentially describe the three sigma bounds or the three sigma uncertainty bounds of, of that. So as you see, as the filter is converging, also the uncertainty is converging, which means that I'm getting more and more confident in my estimate. And that's a very important factor. The other area is that there are parameters in the model, not just the the state uncertainty. The model has constants, or what we assume are constants that are related to the gravity model, the drag model, solar radiation pressure, all perturbations that go into the model. And those uncertainties also are introduced in our propagation. The other thing is that motivates this uncertainty propagation business is that when you look at this plot very specifically, you will realize that for space-based surveillance, there will be gaps in coverage and significant ones because of range, because of lighting, because of tasking too. Now, this problem can be resolved by constellation design, optimization, and so on, which is something that we are looking into. But assuming that, even with all of this, there will still be gaps. And as the gaps increase, you could see that your filter diverge. And that is essentially what motivates looking into these uncertainty propagation. Two approaches that we are looking at is that essentially how to compute the state transition tensors, higher order state transition tensors, and how to approximate the probability density function. And both of them have uses in collision, in estimation, in prediction, and in general, all of that obviously feeds into having better space situational awareness or more robust space situational awareness. So we'll start by looking at the state transition matrix. Several works have been done looking at Cartesian space state transition matrix, some computation techniques to compute the STM with and without perturbations, and also some that have moved the coordinate frame from the Cartesian coordinate frame that we have been looking into to an element-based coordinate frame, which can essentially produce a different set of results or more amenable results. What we have looked at is what we looked at is essentially using a method that is along the lines of automatic or computational differentiation that can essentially compute those values using some recursion functions. And I'm going to show this next, but this is what it could be used for. So if we look at the state transition matrix, and usually we represent this in ASCO by phi, these are the higher orders ones. So this is the first order. This is an n by n matrix. This becomes a tensor, which is n by n by n tensor. And this becomes a fourth order tensor, which is an n by n by n, and so on. So you can see here, this is 6 by 6, 6 by 6 by 6. And the orbit problem, because orbit problem has 6 values. And this becomes 6 by 6 by 6, 3 of them, and so on. So essentially, this is the variation, and the variation in the final state is a function of the variations of the initial state right there. And you could essentially come up with the distribution function of the final state given the initial state through that sort of reversion of the series. And these are the coefficients that you come up with. Now, the inverse of phi can be easily computed because phi has something called it's symplectic. So because phi is symplectic, and we'll discuss this later, its inverse is not as complex as it would look like. But what we have been exploring is a a recursive technique that essentially represent the two-body problem in terms of these scalars right there, an F and G scalar. And we used what is essentially the chain rule, or more generally, the Leibniz rule, to come up with the recursions for these values. Now, if you look at this, I can essentially tailor expand the solution of the position and velocity, but that becomes a function of the higher order like the higher order time derivatives of position, velocity, acceleration, jerk, and so on and so forth. And if I can compute those guys, then I can essentially sub in the Taylor series and I can go to any order. Now, there is and we've published a few papers about this, essentially showing that this can go to up to 25 or 26 order, make bigger jumps in the time, and we even came up with some optimizations to find the best time and the best order combination for an accurate solution. So that was all well and good, and we were able to produce those recursions. And this is what I was just describing about the adaptation of the method, that it essentially come up with the best n, which is the number of terms in that Taylor series, and comes up with the best delta t, which is the distance between each point that we are evaluating at. So that's based on the last two terms in the series and a prescribed relative and absolute tolerances. But this is what we were looking at when we looked at the state transition matrix, is that we can use the same approach to come up with the various elements of the state transition matrix. So the first order state transition matrix right there, which has that superscript 1, is a 6x6 matrix that measures the sensitivity of the position to the initial position, or in this case, just the previous position, and to velocity, and then measure the sensitivity to velocity, to position, and velocity. So if you use the same approach and you expanded the Taylor series, you will get these expansions. Now, we followed the same idea of essentially coming up with the recursions that describe these partials. So you can see here, there is that application of Leibniz product rule for the partial derivatives, or the higher order time derivatives of the partial derivatives, if you see equation 16 and 17. And we came up with those variables. Now, as you go higher in the dimensionality, and you can see that the only term, there's only one term that gets added every time you go up in a dimensionality. And this term, once you know the first value of it, you can essentially keep recomputing the higher order derivatives of it recursively. So with that in mind, we essentially can reproduce what we did in the state variables to produce the state transition matrix, which essentially what we have done here for the first order, as you see in the previous slide. Now the second order, you see it, now we're using that index notation where we have the second partials with J and K, and that what this recursion look like. Now, again, you could see here that from the previous term, there is an additional two terms, but those, all of them can be computed recursively. So we only need to evaluate the first one. Anytime you introduce a term, you just need the first value of it, and then the higher values comes from the recursions, as you see here in R and F and G and so on. So we added some perturbations to the model, and the perturbations are important. The J2 perturbation is one of the most dominant perturbations in the higher orders matrix in astrodynamics, and it accounts for the oblateness of the Earth. Essentially, that the Earth is not a perfect sphere. And basically, we did follow the same approach using Leibniz product rule, and computed the recursions in that perturbation. And those are the set of equations that describe those recursions. We also have several results that show drag that show higher order uh, zonal perturbations, J2 through J6. And we are also now working on more results related to the more general perturbation model. So we tested this idea on several orbits, and you see here the increase of eccentricity means an increase of the nonlinearity of the problem, and obviously the complexity of the computation. I'm gonna skip this because we compared the so without perturbations, there is a closed form solution that we compared against. And this is the approach we have used to essentially come up with a way to validate this method. So we did an RMS error, we did the symplectic check, and this is what I mean by the symplectic property of that matrix is that the first order matrix multiplied by this skew symmetric matrix of the identity matrix multiplied by phi again is equal to J, which is this. So if you want to invert this, you essentially get the inverse of phi it becomes J into phi transpose again. So this is why the inverse of this guy is very simple. Yeah, so that is what we have. And essentially, the higher order symplectic check is that you essentially take the derivative, and that becomes the check that we are looking for, that those two have are equal to 0. So with that being said, we can do this symplectic checks on the perturbed case without drag, because drag is an unconservative force, and symplecticity is obviously connected to Hamiltonian or conservative systems. And also, the other way is when you have an unconservative force, you use error propagation. So you estimate the error via the first order and estimate the error via the second order. And you can see this comes back to the quantification of the uncertainty, because once you can estimate the error, you have an idea about the variation of that variable, and now you can put the uncertainty bounds related to that variation. All right. So we did several checks here for the first order, the second order, double precision, and we are talking 10 orbit revolutions across the board for the checks that we did for all the orbits. So LEO, MEO, GEO, GTO, and highly eccentric orbits. And for to check the accuracy of the method numerically, we even pushed to 10,000 orbit, which is not realistic, and you should not do this for the state transition matrix, but this is just to show that it keeps the simplicity of the state transition matrix up to 10,000 orbits. That check is mainly for the numerical accuracy of the method and not really for any application, as we're going to see later on. So here, when we introduce drag, you can see that as you increase the number of orbits, your values or your estimates or your errors are diverging. They are increasing with orbit. Now we are talking here 10 orbits, which is a very significant uh, extent of the or of the error prediction. And you can see here there's a couple of orders of magnitude between position and velocity estimates throughout the results, so across all results. But as you also can imagine that even though the state transition matrix is symplectic, or as you can also see, even though the state transition matrix is symplectic up to 16 digits, which is the extent of double precision, we still are using digits. We are in the second or the third digits in meters and meters per second in terms of orbit prediction. And that's why for 10,000 orbits, you can see where this is headed. This is not going anywhere in anywhere that is reasonably representing the physics. But again, it shows that in this case, the error is not coming from the fact that the state transition matrix is not accurate. It is coming from the conversions of the Taylor series itself. It has a radius of conversions, and as you extend that measurement, as you extend that period of time, you're accumulating truncation and round-off errors. And those errors cause and this is a property of any numerical method. So I'm going to skip this. This is just to show various orbits with various first and second order uh, approximation. But across the board, you see the effect between, or we're showing here the effect or the advantage of getting an extra 1 or 2 orders of magnitude accuracy when you increase the dimension and when you increase the degree of the approximation. And we're now looking at the arbitrary order problem as well. Now, the other aspect that is, okay, now we have all of this state transition matrix stuff, which goes very well with estimation, as we have seen. There is a covariance matrix, and this covariance matrix can be computed from the state transition matrix. But also, there could be parametric uncertainty, which cannot be captured by this. So if, for example, in the drag case, there is uncertainty in the drag coefficient, which does exist, then we need another way to approximate the uncertainty. Because this business of uncertainty or handling uncertainty using the state transition matrix, as is shown or as is in the name, it is based on the state. It's a mapping of the initial state to a target or final state. So uncertainty in the states gets mapped, but uncertainties in the parameters need a different approach. So you can create a sensitivity matrix, another sensitivity matrix to parameters, but we went with another approach where we are essentially trying to approximate the PDF, the probability density function. So if you have the approximation of, or you can obtain the approximation of the PDF, then you have a description of an analytic approximation. Then you have a description of the uncertainty surrounding any random variable. Now, in the Kalman filter, there's an assumption that these uncertainties remain Gaussian. Obviously, in real life, this is not true. And as you increase the observation times, or as you increase the propagation time, then these uncertainties become less and less Gaussian, as we have seen in the initial orbit distribution problem, where it goes all around the distribution from a small sphere. It becomes this distributed shape surrounding the whole, basically the whole original orbit. So our idea here is very simple, is that we're using the fact that we're using an aspect of Liouville's theorem that if the system is Hamiltonian, then the values of the values of the uncertainties remain constant. So, or the PDF values remain constant. So even if you propagate forward in time, these points forward in time, if you know what their original values are at the initial time, which you should know, you know something about the initial distribution. This can come from the filter, for example. If you're applying a filter, then it will give you an idea about what is the original distribution. Then you can essentially turn off the filter, propagate forward in time, and essentially try to look at or try to approximate the uncertainty. So because of this Hamiltonian nature of the problem, we can do this. And we also address the non-Hamiltonian or non-conservative system of nature of the problem as well. So these are some simple problems to show the applicability of the method on a linear oscillator. And this is how we essentially handled changes in volume or changes in area. So what we did is, and I'm trying to find, yeah, here's what we did. So I'll show you this in a few slides, but what we essentially did is we looked at the volume and n dimension, and we came up with a scaling parameter that scales the original values to newly updated values of a certain scale. And we have done this scale locally across the distribution or across the various levels of the loads. So here we're showing the damping or the damp duffing, and you can see now that the original, what is known as an original Gaussian, is becoming something that is not, this is not a Gaussian distribution. So, and you can see here that this is the trajectory of the damped oscillator. This is the probability distribution, and here we're using a couple of approaches to validate. One of them is that the property of the probability density function is that the total integral has to be, or the cumulative integral has to be equal to 1. So here we're showing the cumulative integral to be close to 1, which gives us confidence in the approximation that we come up with. Now, here, and this is where the problem comes in play, is that we are now including uncertainties in the parameters. So not only uncertainties that are related to the states, the initial states, as we did with the state transition matrix, but here we are introducing uncertainties in the K, in the stiffness coefficient. And now it becomes a 3D problem, and this is how we deal with 3D problems. And you now have a 3D approximation technique where we find points on the boundaries of that shape, propagate them forward, come up with the approximation, propagate backward, find their values inside that ellipsoid. In this case, it's 3D. And then we add uncertainty in the coefficient or the damping coefficient. So here what we're showing here is that this method can actually be applied to not only state parameters, but also or state variables, but also system parameters. So here, this is the method that we are using to modulate or to scale the volume. And you can see here on the left-hand side, this is where we have the initial, sorry, yeah, we have the final time and the initial time. And essentially, we are approximating or coming up with the volume, the difference in volume or scale factor between the connected nodes. So this looks like more finite elements and tetrahedrals, but this is essentially a way that we used using approximation methods to come up with a way to find what happened due to the volume change. Oops. And here, this is the most, or a very significant time, or a very, very significant result is terms of in the not only the accuracy, but also the computational cost of these methods. And we actually have improved over this even further, but this also shows you that we're talking about 2 to 3 orders of magnitude improvement. We're talking about 100 to 1,000 times faster simulation than what you can do with Monte Carlo. Now, Monte Carlo is the way you go if you want to do a again, this is high fidelity approximations. We're not talking about a back of the envelope kind of thing that gives you a quick result. We're talking about high fidelity accuracy. So we're talking about an integral that is accurate up to 4 to 6 digits, which requires Monte Carlo to run for millions and millions of points for 100 to 1,000 times more time than this approach. So this approach lends itself very nicely to reducing the computational cost and improving and while still producing very high fidelity results. Other aspect of this approach is that it's highly parallelizable. You see here, once you start distributing or creating these nodes, you can essentially create a parallel process to back propagate or to propagate these points back in time and find their values separately because they are all decoupled. They are just distribution of nodes or a selection of nodes that we came up with. So even without parallelization, we're talking about this much accuracy. And we can do the same thing with parallelization. I believe that it will maintain the same level of accuracy, and it will be more hardware and implementation amenable than Monte Carlo, even if you were able to, or you can parallelize Monte Carlo, but still the difference here, we're talking about 100 to 1,000 times faster. So with parallelization, we're talking about stuff that can actually be implemented on hardware and not just a supercomputer or a desktop computer in this case. So we move into the orbit problem, and we're using the same techniques. The orbit problem is more nuanced because now it becomes a 4-dimensional problem in the uncertainty domain. So once we have this, we can essentially look at the overlapping of the two PDFs. And if we look at this overlap, what we can do is that we can accurately compute the probability of collision between two objects in space via via analytical relationships, via analytical or mathematical expressions. We don't have to do Monte Carlo and count points and do all this kind of stuff. We can actually integrate in closed form and come up with an accurate number. Now, currently we're working on validating this with real data to see if our prediction can encompass what a real satellite does. And hopefully we will be able to validate this very soon. Now, this work can also be expanded to higher order. And this is some flowchart that shows that the same idea that we use for 1D, 2D, 3D, and 4D can expand it to ND approximations. And this is from a work of a colleague of mine that in my group when I was doing my PhD. So he published this, and we're also studying this to expand our method to higher dimensions beyond ND. So this is most of my talk today about astrodynamics, and this is a main area of research. I'm going to go quickly over some research or another very significant area that we're working on. And I know I'm running out of time, so I'll do this very quickly. We're also exploring dynamics of charged lunar dust. And what I'm showing here, and this is where the connection of this whole research, the three circles that I showed earlier, is that this is a nonlinear dynamical problem, very similar to the orbit problem, to the multi or the n dimension or the n body problem, if you will. You can represent n number of particles as an n body problem or a multi-body problem. And what we're trying to solve here is that existence of lunar dust hanging on the lunar surface due to the rover moving on the surface, due to landing and taking off, due to moving of the motion of astronauts on the surface, or any perturbation, natural or man-made. Now, one could say that this is a natural phenomenon. It happens on Earth, it happens everywhere else. The difference is, as you all know, the moon has no atmosphere. It's in vacuum. So if the dust particles are not moving due to their ballistics or free fall without any other factors, then the formation of these clouds and the motion of these clouds on the lunar surface has to be explained via something else. Not like here, like dust particles hang in with the atmosphere. So the prevailing hypothesis is related to lunar dust charging or electrostatics. And we have been conducting several numerical experiments to look into this phenomenon, try to understand it, and try to understand how these dust particles behave. So these are some videos, but I don't have time. But you can see here we're looking at several particles that, and I think this one is faster. So several particles that have a positive and negative charge, and you can see how they affect each other and how they essentially get attracted and repel each other in that domain or in that space. So we're looking at these simulations to understand how the dust form and move due to electrostatic, due to charging. The other area that is very interesting, yeah, and these are the various simulations that we have been running. So these are typical experiments that are done in this area where you slide particles on a surface and you compute the interactions. So one other area, and I know this is very brief and it doesn't give this work its justice, but we don't have a lot of time. So I know that the other area is that we're not only it is related to these these forces coming from the electrostatic forces coming from the particles having charges on them. It also comes from tribocharging, where essentially tribocharging is essentially the phenomenon that charge is being transferred from one particle to the other via contact. Think of, having a pen or a pencil and you rub it in your hair and you pick something up. So this is electrical electrostatics. So you can think of these things. So we're looking at model-based approaches, and you can see here, this is another famous experiment that we validated uh, using discrete element methods, and essentially a vibrating bed with particles having interaction, mechanical obviously interaction due to the vibrations, and obviously they get charged because of all the friction and all the contact, and you start seeing the behavior of these particles due to tribal charging. So this is another experiment that we're looking at. Now we have went way beyond these elementary results, and we looked into how does lunar dust itself behave in the lunar environment using the appropriate gravity, the appropriate electric fields, the appropriate values for the particles. And what we have found, and I don't unfortunately have a slide to show that here, but what we have found is that the electrostatic forces do affect the lunar dust dispersion and the cloud forming of the lunar dust quite significantly. And we have some sensitivity analyses that shows that, and also some preliminary results that show that the dispersions is several orders of magnitude in terms of the in terms of from the inertial or the initial distribution. Quickly over controls and robotics, we're looking at optimal control problems, guidance in an environment that has obstacles and changing. We're looking in some computational techniques to do this. And finally, this is the robotics portion of the lab. We have several UAVs, several ground vehicles. We're doing experiments that implement some of the control, or we're planning some experiments to implement some of the control schemes that we develop, as well as experiments that uses this platform, which we call Rome, and basically try to emulate space motion. This has good applications in sensing and also to show the orbit motion. As we see here, these are experimental results from the kinematics model, and now we have a dynamics model, and the group has been working very actively in this area. Here are some videos for the ground vehicle doing a circle, and it's very loud, and this is the motion that we can produce with our robotic arm. We now have a new robotic arm that can essentially produce more smoother dynamics than this. Sorry, I went a little bit over. So I'd like to acknowledge all the graduate students in my group. Most of them are here. Thank you for being here. And also undergraduate student researchers, collaborators, and funding. And thank you, and I'd be happy to take any questions. All right.
Either. So if
Okay.
anybody on YouTube has a question, you can type it in the chat.
Yeah, it was a little bit too technical, I think.
It's good to have a variety. We have a large variety of people.
Yeah.
It's been a while since I took Astrodynamics, so it's kind of took it a second to come back to me in the middle of the presentation.
Okay, I'm glad. It's always good to keep these things going, keep the memory fresh. All right.
All right. Yeah, I don't see any questions.
Okay.
Yeah, thank you so much for coming tonight.
Thank you.
Yeah, it was really exciting to see what you guys are working on and all your students there in the lab.
Thank you. thank you all, and I hope this has been insightful. And yeah, hopefully we can do more of these talks in the near future. Maybe I can dedicate another talk about the lunar dust problem and another talk about the controlling robotics problems that we're looking into.
Yeah, that sounds great.
Yeah, I'd
We're also
like
allowed to
that.
have your students as well if any of them
Yeah, most
graduate or
definitely. I think
undergraduate.
this time around they can do a better job in focusing on their areas than what I would be able to do.
Yeah, it'd be great to see what those guys are working on.
Yeah, sounds great.
Yeah, thank you. Have a
All
good
right,
evening, everybody.
you too. Thank you. Bye.
Yeah, well, thank you to Dr. Elgohary for a great presentation. And if you guys have any questions for him, his website is on the page here, mae.ucf.edu/TAE. You can also contact him. His email address is on there, on their faculty page at ucf.edu. For AIAA Central Florida section, if you have any questions or potential speakers you'd like to see in the future, cool ideas for events like this, we're always open to new ideas. We love to have speakers as much as possible about a variety of different subjects in aerospace. So you can contact us at aiaa.central.fl@gmail.com or at any of our pages here, like our Facebook and Instagram, or you can subscribe to our YouTube channel to see more events like this and check out our previous events that we record. They're all available on our channel, usually the day after they go up. So if you can't make it that evening or that day when we host an event, you can always check it out on YouTube later.